Here's an example that we'll be covering in class, but I'd like for you to conceptually see some real-world applications. Say we have a series of points, and we need to find the approximate center of those points. Here's an example. Each one of these points represents a real-world point of electricity delivery. Longitude and latitude locations are given, and you can see how a general shape is made from these series of points. So what we'll do now is use our previously covered method of a convex hull to determine an area, and once we have the area, hopefully determine the center of those points. So just given a general information of a number of points, P of points, a set P where each of these points are real longitude latitudes, we can use convex hull to, such as the Jarvis march covered earlier, where you're kind of wrapping a rubber band around the most outlier points. Now, once you have this area, you can calculate a center point. Center point to look at distances between other similar objects, or you can use that center point to look at distances to other polygons. But how do you know that that center point is very good? Could it be off? Could it be weighted incorrectly? So adding a bit of information, such as a local power company, you can re-estimate individual convex hulls and estimate the center of those convex hulls. So a power company can actually be inside another power company, which is why you have multiple X's inside some of these polygons. And now you've actually cleared out some white space, some empty space, and hopefully can get a better estimation of the true center. So this is what we looked like before, just attributing everybody to one bucket, to TVA. Here, we've attributed the correct points to the appropriate power companies, represented by each of these different purple polygons. Once we have these polygons, we can find the center of centers, if you will, every X here. And here's the difference. So again, the red line represents our every point taken into account equally. This was that center. Now the triangle is the center of centers, if you will. So we're trying to eliminate this white space and not count it as showing up as one of these denser spaces. And triangle represents our new calculated center, which is a much better estimate than the X. And why is this important? Because if you were looking at distances to weather or distances to other geographic ranges, being hundreds of miles off will make a significant difference in how you attribute weather effects or other geographical information. So this element combines a few different points that we will go over in class, such as intersecting lines, convex hulls, and a little bit of data information. Thank you.